3.7. Before we get started on notes, I just want to show you something real quick. And that is that here in 3.73, I don't have in-class examples because 373 just repeats 1 and 2. There's like nothing new in this section. So instead of in-class examples, what I put up here for you is this one-page PDF that is my handwriting. This is from a time when I was teaching this class live a couple years ago. And my class was like, this is too many rules. And I was like, it's really not that many rules. Let's write them all down together so that you can see that it's really not that many rules. So these are all of the rules that you need to know about rational functions, all right here on one page. My handwriting's not the best, but you'll figure it out, I think. So I would definitely recommend downloading this or keeping it near you, you know, like putting it on your computer, printing it out, whatever you want to do, because that is, again, just it's everything that you need to know about rational functions all in one spot. Okay? Because I do feel like the rules here can seem overwhelming, but maybe when you see them all just listed out like that, it's not quite as bad. So domain of a rational function is something that we've talked about before. We know that we cannot have a 0 in the denominator of a fraction. So the domain of a rational is all real numbers except the values that would make the denominator 0. So here to find those values, I'm going to take that denominator and I'm going to set it equal to 0 and solve so that I can find the values that would make the denominator 0. Now this one does not factor. I know that there are not two numbers that would multiply to negative 36 and add to 1. So I'm going to use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac. Okay, over 2 times a. And they're asking me for decimals. So to get the decimal of that, I'm just going to put it in the calculator. Remember that anytime we're putting something with like a numerator and a denominator, like anytime you're putting a fraction like this, you want to make sure that your denominator has its own parentheses and your numerator has its own parentheses. So the -1 minus that. So my two values that would make that denominator 0 rounded to 3 decimal places would be negative 1.630 and 1.380. So all real numbers except those two. And so then in interval notation, I would say all of the numbers to the left of negative 1.630, all of the numbers in between negative 1.630 and 1.380, and all of the numbers to the right of 1.380. And again, we've done examples like that before, just like that before. So this part of it shouldn't be new. Now, here, I'm going to do the exact same thing that I just did and set the denominator equal to 0 and solve. When we're solving a polynomial, as I mentioned in our polynomials unit, usually the easiest way to go about that is to graph it. Start with a graph, get any roots from the graph, and then, really? Okay, 8x to the 4th. And then after you have all of the 34x to the, after you have everything that you can out of a graph, you do synthetic division to get those values, to divide those values out, and then we see what we can do with what's left. X to the 4th minus 34x to the 3rd plus 25x squared x plus 60. Okay, let's take a look at it. So I see a 0 at 2. I think. I always double check them in the table just because it makes me feel better. So I see a 0 at 2, and that 0 looks like it's bouncing. And we know that when a 0 is bouncing, that means it's repeated. It happens twice. So I'm going to be able to use synthetic division with that 2 and take it out twice. And so again, since it was a bounce, that means that the root repeats. And so if this was a to the 4th, then this is a to the 3rd. And what I have here then is a squared. So I have a squared minus 2a minus 15, and I want to set that equal to 0 and solve. So does this factor? Well, 8 times 15 is 120, so I'd have a negative 120. Two numbers that multiply to a negative 120 and add to a negative 2 would be negative 12a and a plus 10a. And so then I could GCF out of 4a, 2a minus 3. Here I could GCF out of 5, 2a minus 3. So I have 2a minus 3 and 4a plus 5. So now my zeros are 2, which we knew from the graph. If I set 2a minus 3 equal to 0 and solve, 3 halves. And if I set 4a plus 5 equal to 0 and solve, negative 5/4. So again, this question is asking for decimals. So I'm going to convert these to decimals. So this is all real numbers except negative 1.25, 1.5, and 2. You don't have to put them in order, but I like to because then when I'm doing interval notation, they're already lined up for me because interval notation, they do have to be in order. So all of the numbers to the left of negative 1.25, all of the numbers in between negative 1.25 and 1.5, all of the numbers in between 1.5 and 2, and all of the numbers to the right of 2. Okay. When we're looking for a horizontal asymptote, we have 3 scenarios. So our 3 scenarios are that you have a bigger degree on the bottom, and in that case, your horizontal asymptote is y equals 0. You have the same degree top and bottom, and in that case, you use the leading coefficients. You have a bigger degree on the top. In that case, you do not have a horizontal asymptote. So these are the 3 rules. So we look at this rational, and we ask ourselves, does this have a bigger degree on the top, on the bottom, or are they the same? Well, in the numerator here, we have a linear, so that's a degree 1. In the denominator, we also have a linear, so that's also degree 1. So since we have the same degree top and bottom, we use the leading coefficients to decide what our horizontal asymptote would be. So here, remember when there's no coefficient, it's 1. So here my horizontal asymptote would be negative 2 over 1 or just negative 2. And that horizontal asymptote is what describes the end behavior for us. So if you're ever asked end behavior, or you will be, we're going to see one in just a second, then know that this would be that it approaches -2 on both the left and the right. Okay. And so if we're continuing to look for end behavior, well, that still just means to find the horizontal asymptote. So here in this first one, we have the same degree top and bottom. So we would use the leading coefficients. So that means the horizontal asymptote on that one would be 1, because it would be 1/1. Now on the next one, we have a bigger degree on the top. And when you have a bigger degree on the top, you do not have a horizontal asymptote. And on this last one, you have a bigger degree on the bottom. And when you have a bigger degree on the bottom, your horizontal asymptote is always y = 0. Okay. I want you to be careful when you're working on these on your homework, because not all of them are in standard form already. A bunch of them are like weirdly out of order. So please make sure that both your numerator and your denominator are in standard form before you start looking for your horizontal asymptote. So here we have the same degree top and bottom again. So that means we're going to use those leading coefficients. So I would have a horizontal asymptote of 2/3. And so what that means is that on the right side, as r approaches positive infinity, f of r also approaches positive infinity. And on the left side, as r approaches, what am I doing? 2/3. And on the right side, as r approaches negative infinity, f of r also approaches 2/3. So anytime your horizontal asymptote is a number, including 0, then you're on the top and bottom always approaching that number. On the left and right, I should say. Okay. So in order to determine the horizontal asymptote for this one, we have to figure out what the degrees are. So remember, in factored form, to find the degree, we add. So 3 + 7 is 10, and then 16, and then 24 on the top. 5 is 12, 17, 21 on the bottom. So a bigger degree on the top means that there is not a horizontal asymptote. And your end behavior here then depends on your leading coefficients. If you have a positive leading coefficient, then your end behavior looks like this. If you have a negative leading coefficient, then your end behavior looks like this. So a negative leading coefficient here means that as t goes to the right, p of t goes down, and as t goes to the left, p of t goes up. So then in 372, we talk about some other properties here, or the rest of them, I should say. So vertical asymptotes are one of the possibilities of something that happens at your excluded values. So we know that when we find the domain of a rational function, we get these values that are excluded from the domain. Most of the time, excluded values are vertical asymptotes. So for example, right here, I know that I can't put 3 into this function, because if I do, I'd have 0 in the denominator. And then that, I guess this should be an A, that 3 is then a vertical asymptote. It's a line that the graph gets really close to, but never touches, it never crosses. Okay, so excluded values from the domain. One of two things happens when you have a value excluded from the domain. You either get a vertical asymptote like this, or you get a hole. So holes happen when you cancel a factor. And if you look back at my notes, you'll see that the very first thing that I wrote here is reduce if you can. So you should always reduce first. If you can reduce, reduce. That should always be your first step. And so here I can reduce this 7r minus 4. And the minute that I make that reduction, I create a hole. So here, to find the location of the hole, I take that factor that I canceled, I set it equal to 0, and I solve. And this is the x value of my hole. To find the y value of my hole, I take this, the x value, and I plug it in to my reduced rational function. You have to plug it into the reduced rational function. If you plug it into the original rational function, you're going to get an undefined error because you're going to get a 0 in the denominator. So -7 times 4/7 minus 5. Oop, I forgot a very critical part here. I need an extra set of parentheses in front because the numerator has to have its own parentheses and the denominator has to have its own parentheses. So times 4/7 minus 6. And then the big parentheses closes out the numerator. 5 times 4/7, 7 to the third. 4/7. Nope. 8. Big parenthesis to close out the denominator. So then my whole occurs at 0.571, negative 0.556. Okay, so once you have your whole figured out, everything else that you do to the reduced fraction, to the reduced rational. So my r-intercepts are the places where my numerator equals 0. So I take my factors left over after I reduce, and I set them equal to 0 and solve. So my first r-intercept is -570. And then if I set r minus 6 equal to 0, I'll just get 6. My vertical asymptotes, happen at the places where my denominator equals 0. Again, that is after my reduction. So if I set 5r plus 7 equal to 0, I will have -7/5. If I set r minus 8 equal to 0, I will have r equals 8. And my h of r-intercept is where r equals 0. So I'm going to go back to my rational and I'm going to plug in 0 for r. So if I put a 0 for r right there, that -7r is going to go away. And I'm going to have -5 to the third times, plus. I put in 0 right here, that's going to go away, times -6 divided by, put a 0 in for r here, and I'm going to be left with 7 to the third times -8. So then my r-intercept is at 0, -2.73. So we're going to do one more like that, only given standard form. And so just like the problem that we did before, I'm gonna have to get factored form here. I guess not exactly like that problem, but in order to get factored form, the fastest way, honestly, is to find the zeros using the way that we did before, and then turn the zeros into factors. So I'm going to do my numerator and my denominator separately. So I have 5t to the third plus 6t squared minus 29t minus 6. X to the third, 6x squared. Oops. Minus 29x minus 6. So let's graph this. Looks like there's a good one at -3, and maybe another one at 2. -3 and 2. Okay, so take out the 0 at -3. What did I do? That's not 16, that's 6. -9, 27, there we go. 6, okay, and the other one was at 2. Okay, so if this was to the third, this is to the second, so then this is just a regular t. So factored form of this numerator then would be t plus 3, t minus 2, and 5t plus 1. T plus 3, t plus 2, 5t minus 5t plus 1. So we're going to repeat that for the denominator. T. Just putting this in completely wrong. Come on. 10x to the fourth. It's 33x to the third. It's 13x squared. It's 24x plus 4. Okay. Okay, it looks like I only have one good usable 0 at 2, but the good news is that that looks like it's a bounce. Okay, I do have a 0 at 2. I always like to double check again because I want to make sure that it's actually on that and not just really close. So I do have a 0 at 2, and that 0 is a bounce, so I know I can divide that 2 out twice. Okay. So then if this was 10 to the fourth, then this is 10 to the third, and this is 10 squared. 10t squared, excuse me. And so I have 10t squared plus 7t plus 1, and that will factor. Two numbers that multiply to 10 and add to 7 are going to be 5 and 2. So these have a 5t in common. I'll leave me with a 2t plus 1. So I have 2t plus 1, 5t plus 1, and then t minus 2, t minus 2. Now you see why we do polynomials right before we do this. Okay, so here I am. Again, I need to cancel factors, so always reduce. That is always going to be your first step. And so when I reduce, I'm left with t plus 3 over t minus 2 times 2t plus 1. Now, I want you to notice that I canceled the t minus 2, but there is still a t minus 2 left. So if this happens, then that t minus 2 is not a whole, it's a vertical asymptote. Okay, so if it's, oh, I canceled it, but I didn't cancel all of them, then that vertical asymptote wins. Okay, but I do have one whole, and that was at this 5t plus 1 that I canceled. So I do have a whole at t equals negative 1/5. Now let's find the y value of that whole. So the negative 1/5, negative 1/5. Negative 1/5 plus 3 divided by negative 1/5 minus 2. 2 times negative 1/5 plus 1. So then my whole is at, that would be negative 0.2, 2.121. My zeros, or single zero, I guess, would be at negative 3. Because if I set this equal to 0 and solve, I'd have it t equals negative 3. My vertical asymptotes would be at, if I set this equal to 0 and solve, it would be 2. If I set this equal to 0 and solve, move that, so negative 1 divided by 2, negative 1/2. And then what letter was this? F of t. My f of t, or y-intercept, would be where t equals 0. So if I plug a 0 in for t, I would have just a 3 in the numerator. And negative 2, I guess just a 1 on that side, huh? So negative 1.5. So what we're going to do here is, with this graph, we're going to backwards design an equation based on everything that we know. So here's what I know. I know that a 0 at 0 and a 0 at 3 mean that my numerator had to have an x and an x minus 3. I know that an asymptote at negative 1, a vertical asymptote at negative 1, and a vertical asymptote at 5 means x plus 1 and x minus 5 in the denominator. I know that a horizontal asymptote of 2 means that, number 1, I have the same degree top and bottom, which I do. I have quadratics both top and bottom. And that my leading coefficients must have been 2 over 1. So I already have a 1 down here, so I really just have to add a 2 there. That should be it. And so then we're going to do the same thing down here. A vertical asymptote at 2, so that's in the denominator, plus 2, and -2 means x plus 2, and at 1 means x minus 1. X-intercepts at -5, so that's x plus 5, and +5, so x minus 5. And then a horizontal asymptote of 4 means that I need to have a 4 in the numerator.